So we are very pleased to have Jinyoung Park from Stanford University. She's now famous in Korean newspapers, important newspapers, about this solving this conjecture by Kahn and Kalai. And she will. So today and tomorrow she will talk about that conjecture, right?
Yes.
Yes, please.
Okay. Thank you very much for this invitation. It's my great pleasure to give a talk at IBS. Okay, so the title of this talk is Thresholds, and okay, so this is my plan for today. In this talk, I'll introduce the Kahn-Kalai Conjecture, which is a central conjecture in probabilistic combinatorics, and then we're going to discuss our results related to this conjecture. But for that, we first start with a brief introduction to random graphs, just to begin with a concrete picture in mind. And also, historically, random graph theory was the starting point for our entire story. But later, we'll see that the setting of our work is much more general, and we'll get there. So let me first introduce a little bit about random graphs. Okay, so GMP is as usual, GMP is the Erdos-Urani random graph, and the vertex set of GMP is this bracket n, which means the set of integers from 1 up to n. And here we think n is finite, but very large, like 100, 1,000, or 1 million billion. So because we have n vertices, so that means how many potential edges do we have? Just to check, we're on the same page. How many potential edges do we have?
And choose 2.
Yeah, n choose 2. So we have, we have n choose 2 edges, and then each potential edge is included with probability p independently. So for example, if we have n equals 3 and p equals 1/2, then we have those 8 graphs in our sample space. And because p is 1/2, so that means each graph in this sample space has the equal probability, 1/8. But we can adjust our p. So for example, if p is very close to 0, like 0.0001, in that case, the sparse graphs are much more likely than the denser graphs. On the other hand, if p is closer to 1, then the dense graphs are much more likely. So in fact, GMP is not a fixed graph, but this is a probability distribution. So it makes sense to ask questions such as, what's the probability that GMP is planar? Or what's the probability that GMP is connected, etc.? And in those questions, we are not exactly interested in finding the precise probability, but instead, what we are more interested in is the typical behavior of GMP. So if we consider the entire sample space, what's the typical behavior of our random graph GMP? Okay, and then, so for that, we use WHP with high probability. And when we say GMP does something A with high probability, then this means the probability that GMP does A tends to 1 as n tends to the infinity. And in this setup, usually P is a function in n. So if n tends to the infinity, then P also tends to 0. That's our usual setup. Okay, do we have any questions so far? Okay. So then let me talk about evolution of GMP. One striking thing about GMP is appearance and disappearance of certain properties are abrupt, and this gives us the notion of thresholds. So in this evolution of GMP, we usually think of this as we add edges 1 by 1 at random. So when p is 0, then no edges are present, so we have this like empty graph. And at the end, when p is 1, all of the edges are present, so we have this complete graph. And we increase p from 0 to 1, and we think of that as we add random edges 1 by 1 each time. So then we observe the typical behavior of GMP as we choose edges 1 by 1. And so for example, let's consider what's the typical maximum size. Here I used this typical because again, GMP is not a fixed graph, but this is a random distribution. So what's the typical maximum size of connected components of GMP? Here what's interesting is if n times p is slightly smaller than 1, then typically all of the components have size at most log n. So here this is up to a constant vector. So all of the components are pretty small. On the other hand, if n times p is slightly larger than 1, then suddenly we see a giant component whose size is as large as in the order n. And so in this sense, we can say that p equals 1 over n. This is more like the threshold for the appearance of a giant component. And this is just one example, so this is called the threshold phenomenon. And so this is just one example, and for many other properties, we see this abrupt threshold phenomenon. So then it became a natural, so it was very natural that our central interest in probabilistic combinatorics is to find thresholds for various properties, not just giant components, but for many other properties. So here I put some of the test results on finding thresholds, and I'm not going to read all of the things in the list, but I just want to show my audience that so this finding thresholds is really like long-studied area, and many people have studied those problems pretty intensively. And one more thing that I want to point out is when you look at the list, the study has been done mostly for specific properties, such as like connectivity or like Hamiltonian cycles, so containing Hamiltonian cycles. And so later we will see that the Kahn-Kalai conjecture is the effort to put all of those specific properties in a general framework. We'll get there soon, but okay, so this is a brief introduction to random graphs, and in the next part, let me define thresholds. Are there any questions so far? Okay, then let me define thresholds. And as I said in my earlier slide, our work is in more in general setting. So here we use X for a finite set, and this X can be anything. We don't have to. We don't necessarily stick to random graph theory. But here X is just any finite set, and as usual, 2 to the X is the power set of X. Okay. And we use mu p for the p-biased product probability measure on 2 to the x, which means for any subset A in X, mu p of A is defined to be p to the size of A times 1 minus p to the size of the complement of A. And we use xp for the random variable whose distribution is mu p. And so this is called p random subset of X, and simply speaking, xp is just a random biased coin flip. So we have X, we have our entire set X, and for each element of X, we just flip our biased coin with the probability for head is p. And this experiment is independent for each element. So this is our p random subset of X, xp. And one example is this. So what if we take X to be n choose 2, which is the set of edges in the complete graph? In this case, xp is simply GMP, right? Because we have n choose 2 edges, and we choose each edge with probability p independently. Or, so this is the Erdos-Urani random graph, or it can be viewed as the edge percolation on the complete graph Kn. So this is just one example. And so as we take different x's, xp can be just any random discrete structure. So another example is this. If we take x to be the collection of all of the k clauses from n variables, in this case, xp can be viewed as a random CNF formula, which is an important object in computer science. So x really can be anything. And next, we use calligraphic f for an increasing property. And so, yeah, the definition of an increasing property is this. Whenever something contains an element in f, then this thing is also contained in f. In other words, an increasing property means we can't destroy this property by adding elements. Okay? So here on the right-hand side, I draw the picture of an increasing property. So this circle is the picture of 2 to the x with the natural process structure. So we have the empty set at the bottom and the entire set on the top. So that means in the first layer, we have all of the singletons, and in the second layer, we have all of the doubletons, etc. So an increasing property means whenever we have an element in F, then everything that contains this element is also in F. So this is an increasing property. Okay, so one example is this. In the first example, if we consider X to be this and choose 2, then the collection of all of the connected graphs, or the property to be connected, this is an increasing property, right? Because because adding an edge does not destroy this property. And another example is to contain a triangle. And let me skip the second example and move on to the next slide. So in the next slide, I'm going to define thresholds. A well-known fact is that for any increasing property F, which is not the empty set or the entire collection, we just exclude those things to avoid triviality. So for any increasing property F, mu p of F, which is by definition the probability that xp, our random object, satisfies the given increasing property F, this is continuous and strictly increasing in P. Let's just think about one easy example. So let's say F is the graph connectivity. In this case, if P is 0, then G and P is just the empty graph with probability 1. And in that case, what's the probability that G and P is connected? Simply 0. So that means we are here when P is 0. On the other hand, when P is 1, in this case, G and P is just a complete graph. And what's the probability that G and P is connected in that case? That's 1. So we are here. And as we increase P from 0 to 1, the probability that G and P is connected also increases from 0 to 1. So that's the meaning of this graph. And because this graph is continuous and strictly increasing in P, so there must exist something that's called PC of F, for which mu P of F is exactly 1/2, right? And this PC of F is called the threshold for the given increasing property F. Okay? But here, 1/2 is not really important. What's important is, so the rough meaning of the threshold is, if we are below this threshold, then it's unlikely that our random object xp satisfies the given increasing property F. On the other hand, if P is larger than threshold, then it's much more likely that our random object xp satisfies the given increasing property. So this threshold is really the threshold for this threshold phenomena. Okay, so this is the definition for thresholds, and I wonder if there's any question about the meaning, because I don't want to lose my audience in the first part of my talk. So are you okay with the definitions?
Are there any artificial property where the probability is like mostly 1/2, above 1/2, and then suddenly jump to?
Yeah, that has to do with sharpness of thresholds, and we'll get there soon. But
Okay.
I'm not going to talk about it. But yeah, that's also one very interesting area of this. Okay, are there any other questions? Okay, so are we okay with the definition of thresholds? Okay, good. So it's in the next slide. So there are two interesting directions of study of thresholds. The first direction is called sharpness of thresholds. And roughly speaking, this asks how steep this graph is. So we see like here, how steep this graph is. That's called the sharpness of thresholds. And I think this answers Professor Ohm's question. So this is one direction, and this is a very interesting area, and there are many interesting results. And most of the work is based on Fourier analysis, but we are not going to talk about this direction. But what we are interested in is the location of thresholds. And historically, most of interesting work was on thresholds for specific properties, just like as we saw in the previous list. And the Kahn-Kalai conjecture suggests a general bound, which implies some of the known results. So roughly speaking, the Kahn-Kalai conjecture says this. So we are interested in the value or the location of the threshold for the given increasing property. Let me call this PC of F. And there is something called there's something called the expectation threshold, which always gives a lower bound on the location of thresholds. And the Kahn-Kalai conjecture says that the location of the threshold is at most this easy lower bound times some tiny error term. So if this conjecture is true, then the location of the threshold is trapped between this narrow window. That's the meaning of the Kahn-Kalai conjecture, and so this is our new result.
So this error term depends on if or...
Oh, this error term depends. We'll get there. Yeah, it's a little bit. It needs a little bit of definition, so but we'll get there. And so, so the fundamental question behind this conjecture is this: what drives the threshold? What drives the location of the threshold? And we're gonna look at 4 examples. And throughout those examples, what we want to do is to build up some observations to see why this conjecture makes sense or where this conjecture came from. Okay, so in the first example, okay, so our x is n choose 2, so that means xp is just the GMP, and let's say our increasing property is to contain a copy of h, where h is this little graph. H has 4 vertices and 5 edges. And our question is, what's the threshold for GMP to contain a copy of H? Okay, so, and to answer this question, the usual suspect is the expectation calculation, because in this question, we are interested in the number of copies of H in GMP. And because GMP is a random variable, so the number of copies of H in GMP is also a random variable. And if we want to work with a numerical random variable, then the very first thing that we want to examine is its expectation. It's a very natural approach. So we start with the expectation calculation, and if we compute the expected number of h's in GMP, then it gives n to the 4 times p to the 5. This is up to a constant factor, so we ignore all of the constant factors. Here n to the 4, this is because H has 4 vertices. So the number of potential copies of H is about n choose 4, which is about n to the 4, if we ignore constant factors. And here, p to the 5, what's this? This is because H has 5 edges. So that means the probability for each copy of H to exist is p to the 5. So the expected number of copies of H's in GMP is n to the 4 times p to the 5. Are you okay with this computation? Okay, and then this quantity tends to 0 if p is much smaller than n to the negative 4/5. And this quantity tends to the infinity if p is much larger than n to the negative 4/5. So in this sense, we can say that the threshold for the expectation for this random variable is about n to the negative 4/5. And here I use this quotation mark because I haven't defined it yet. And later we'll see the rigorous definition of the expectation threshold. But for now, let's just feel this with our heart. So the threshold for the expectation is about n to the negative 4/5. Okay, and this computation gives us a trivial lower bound on thresholds, because so here we have this p n to the negative 4/5, and what we know is if p is much smaller than this quantity, then the expectation tends to 0. So that means x is 0 with high probability. So typically, we do not see any copy of h's. So by the definition of the threshold must be at least as large as n to the negative 4/5. Okay? And it turned out this trivial lower bound is actually the truth. So the truth is equal to this trivial lower bound, and the proof of this the proof of this statement uses the second moment method, but let me not talk about the details. But after we observe this first example, maybe one can dream that the expectation calculation predicts the location of the thresholds. So this is the first observation. So let me examine some more examples to confirm our hope or our dream. So this time, x is still n choose 2, so that means xp is GMP. And this time, our increasing property is to contain a copy of k, where k is this little graph. And notice that this is our h in the first example. So this is h with a little tail. And the question is the same. What's the threshold for GMP to contain a copy of k? So as we did before, we start with the expectation calculation. And if we compute the expectation, then it gives us n to the 5 times p to the 6, because k has 5 vertices and 6 edges. Okay? So the threshold for the expectation is about n to the negative 5 over 6. And this gives us a trivial lower bound, just like we discussed in the previous slide. So our question is the threshold actually equal to this trivial lower bound? And what's your guess?
Yes.
Yes? No?
Probably not.
The answer is no.
Otherwise, you wouldn't put it through.
Yeah.
So in this case, the truth is n to the negative 4/5, which is much larger than the lower bound. So here, the expectation, the lower bound from the expectation is n to the negative 5 over 6, but the actual threshold is actually much larger. And do you see why? Why n to the negative 4/5 must be truth? This is because, so what's this? Do you still remember what we saw?
The graph H.
Yeah, this is the expectation threshold for H. And we know that if P is much smaller than this, then typically there's no H. And because H is a subgraph of K, so if there's no H, then there's no K. Okay, so in this case, from this example, we learned 2 lessons. The first lesson is, okay, still we can predict the location of the threshold using some expectation calculation. But the second lesson is the expectation calculation is not just naively for the entire graph, but more like the densest part of the graph, the core part of the graph. So it looks like, as long as we look at the like right thing, then the expectation calculation for this right thing gives us the threshold. And in general, that is true in some case. So this is proved by Erdős-Renyi and Golobash. And roughly speaking, it says that for fixed graph K, the threshold is equal, up to constant factor, is equal to the threshold for the expectation of the densest subgraph of K. So if K is a fixed graph, then our observation from the second example is true. Okay? But something happens in the next slide. But are there any questions so far? Okay, so in the previous example, we considered a fixed graph. So in this example, we consider a growing graph. So here, X is still n choose 2, but F is to contain a perfect matching, where a perfect matching means this. This is a set of disjoint edges that covers all of the vertices. This is a perfect matching. And the question is, what's the threshold for GMP to contain a perfect matching? So we start from the same place. The expected number of perfect matchings in GMP is like this. Let me skip the computation, but from this computation, we know that the threshold for the expectation this time is about 1 over n. So 1 over n is again a trivial lower bound. So we can ask this question, is the threshold equal to this trivial lower bound, 1 over n? And the answer is no. The truth is the threshold for a perfect matching is log n over n. And unlike the previous, so in the previous example, we saw that if we consider the right thing, then the expectation calculation gives us the right threshold. But in this case, whatever subgraph of a perfect matching we consider, it always gives us 1 over n. So here, we do see this log n gap between the trivial lower, between the threshold for the expectation and the actual threshold. So our dream is gone. But we don't give up. What do we do next? We try to understand why this happens, right? So let's think about why we see log n over n. So let me remind you where we are. So the threshold for the expectation this time was 1 over n, but the actual threshold was log n over n. And actually, this log n over n is not something mysterious, but this is another trivial lower bound on the threshold. And this is because of this fact that if p is much smaller than log n over n, then typically GMP has an isolated vertex. And if there is an isolated vertex, then of course there is no perfect matching, right? So this is another trivial lower bound, and this is basically because of the coupon collector behavior of the random graphs. So let me remind you what coupon collector problem is. So the problem is each box of cereal contains a random coupon, and there are n different types of coupons. And then our question is, how many boxes of cereal do we typically need to buy to collect all of n coupons? And here I wrote typically because if we are unlucky, then it will take forever. But we don't consider that unlucky case. But typically, how many cereal do we need to buy? And do we know the answer?
Yeah, like n log n.
Oh, good. Yes, the answer is n times log n up to a constant factor. Now, how does this relate to our problem in random graph setting? So in our random graph setting, our vertices are the coupons. So we have n coupons, which is n vertices. And because of the coupon collector problem, if we have the number of edges much smaller than n times log n, then typically there are uncollected coupons, which means isolated vertices. But this time when we draw an edge, we collect two coupons at the same time. So a little bit different, but it's the same thing. So, and this corresponds to our p much smaller than log n over n. Because we have n choose to potential edges and we ignore constant factors. Okay, so this gives us this easy fact like here. Okay, so this is, we usually say this is the coupon collector behavior of the random graphs. Oh, I should be more careful. So that is not an official term, but we just say that. Anyway, so are there any questions so far?
What about nearly perfect match?
Sorry?
What about nearly perfect match?
Nearly perfect match. That's a very good question. Let's talk about that at the end. Okay, that's a very good question. Okay, so this is one last example. Here we consider a perfect hypergraph matching. So now x is n choose r, not n choose 2. This means we still have n vertices, but this time we consider all of the n tuples, r tuples. So potentially we have n choose r tuples, and xp is random r uniform hypergraph, which means we choose each tuple with probability p independently. So this gives us random R uniform hypergraph, and we call this HRNP. And the question is the same. So this is called Shamir's problem from 1980s, and this problem was open for about like 30 years. It was not just open, but notoriously open. So the question is, when R is strictly larger than 2, what's the threshold for HRNP to contain a perfect matching? And here, a perfect matching means it's the same thing. So this a disjoint union of R tuples that covers all of the vertices. Okay, so this is the question. And when R is 2, the answer was easy. This was proved by Erdős and Renyi already in 1966. And so the reason why R equals 2 case was easy is because there are Hall's theorem or Tuss theorem. But when R is larger than 2, there is nothing analog to Hall's theorem or Tuss theorem. So somehow when R is larger than 2, the problem was much harder. And okay, so just to have some feeling, let's think about this. Okay, let's try something that we did before. And for concreteness, let's fix R equals 3. In this case, if we consider the expectation calculation for the number of perfect matchings in HR and P, then this gives us the threshold for the expectation about n to the negative 2. So this is the first lower bound on the threshold for containing a perfect hypergraph matching. And if we consider this coupon collector behavior, which means we want to raise the probability so that there is no isolated vertices. In this case, we have the second lower bound, which is log n over n squared. And it turned out the answer is equal to the second lower bound. So this was proved by Johansen, Kahn, and Wu in 2008. And so in this case, we see this log n gap again. So far we have seen 4 examples, and so let me summarize our observations so far. So we have some trivial lower bounds on the threshold. And from the first 2 examples, we saw that the threshold for the expectation gives us the first type of lower bound. And from the last 2 examples, we saw that the coupon collector's behavior, this pushes up the first lower bound by log n. Okay, so usually there are some easy ways to get a lower bound on the threshold. And historically, in many, many interesting cases, the main task is to find a matching upper bound. So usually finding an upper bound is hard. Matching upper bound is hard. then the Kahn-Kalai conjecture says that this is a rough statement, and we'll get to the rigorous statement later. Roughly speaking, it says for any increasing property, the threshold is at most log x times the expectation threshold. So you see that if this conjecture is true, then here we have PC of f. It says that and PE, the threshold for the expectation, is a lower bound. And if this conjecture is true, then the location of the threshold is trapped between PE and PE times log of the size of x. And here log of the size of x is really tiny compared to the other terms. So this is a small error term that I mentioned in the first part of my talk. And also, okay, and let me emphasize that this is a very strong conjecture. So for example, this immediately implies historically very hard questions. For example, threshold for perfect hypergraph matchings, which was proved by Johansen, Kahn, and Vu. So this was a very hard, I think I forgot to mention this. Johansen, Kahn, Vu result was very hard. And okay, so the argument itself is hard, and yeah, it was open for a while, and then they received the Fulkerson Prize from this work. So this was a famous work. But if the Kahn-Kalai conjecture is true, then the proof is just one line, because we can easily compute that the expectation threshold is n to the something, n to the negative r minus 1. And if the Kahn-Kalai conjecture is true, then it gives us an upper bound, which is this. And this matches the lower bound, the second lower bound. So that's why the Kahn-Kalai conjecture was believed to be not true, because this is just so strong. And also there's another very hard result, which is immediately implied by the Kahn-Kalai conjecture. And also, so this is called the tree conjecture, but so this is the threshold for bounded degree spanning trees, and it was proved by Montgomery in 2019. And again, this was very hard result. And also, those two results are not very much related. So for example, we have Montgomery's result, but we cannot use his technique to prove Johansen, Kahn, and Vu, or vice versa. So they use very different techniques for their own problems. But if the Kahn-Kalai conjecture is true, then it just gives this general framework that gives those two results immediately.
Is the Johansen, Kahn, Vu's result for any R?
Oh yes, for any fixed R. Yeah, not growing R. Okay. Okay, so I think, yeah, I've advertised the Kahn-Kalai conjecture enough. Are there any questions?
Can you always derive a lower trivial low bounds for F?
Could you say that again?
Can you always derive a trivial low bounds?
Yeah, so for any given increasing properties, the expectation threshold gives a lower bound. But sometimes the computation of the expectation threshold is hard. But for those examples, the computation is very easy. Yeah. Okay. Any other questions?
Then with the coupon collector type of argument, this Kahn-Kalai conjecture implies the Samides problem, hypergraph.
Oh yeah, sure. That's what I said here. So if we assume the Kahn-Kalai conjecture, then from this computation we have this upper bound, which matches the lower bound from coupon collector. Yes. Any other questions? Yes.
Is there any increasing property which captures the rather than the log x, for example, log x?
Yes. Yeah, we'll get there at the end if we have time. Any other questions?
What's the tree conjecture?
Oh, so this is it's written here. Threshold for bounded degree spanning trees. So for example, if I'm given a fixed type of spanning tree, then what's the threshold for GMP to contain that given type of like optimum isomorphism, that given spanning tree, not just any spanning tree, but the given spanning tree.
And if the given spanning tree has bounded maximum degree.
Yeah. So it was surprising that the threshold for that spanning tree was open until 2019. Yeah. And if we do not assume the bounded degree, then this problem is still open. Okay. Any other questions? Okay. And let me move on to the next part. Okay, so then let me give you the rigorous definition of the expectation threshold, and the problem is this. So far we've considered some concrete examples of the increasing property, and there it was very easy to see whose expectation we want to compute because we see who are there. But for abstract f, it's unclear whose expectation we want to compute because our increasing property is just can be anything. So it's not clear what's the minimal element of f. It's just anything. So we need a careful definition for the threshold for the expectation. It doesn't move. Okay. Okay. So before I give the rigorous definition, let me start with an observation. So this observation is about a lower bound on the threshold, and so we know that Q gives a lower bound on the location of thresholds if there exists this G, which is a subset of the power set that satisfies those two properties. The first property is called G covers F, and I think it's better to give you the picture. So let's say this is F, and G covers F means G usually looks like this. This is not an increasing property. This is just a hypergraph. And if we collect everything that's above G, like this, and if everything above G contains F, then in this case we say that G covers F. Are we happy with this? So if we collect everything, okay, so in other words, this means whenever we have an element in F, if we look down, then it contains at least one member of G. This is the meaning of G covers F. Okay, so this is the first property. And the second property is if we add up Q to the size of S for all of the members in G, then this must be at most 1/2. Here 1/2 is not very important, but this 1/2 corresponds to the 1/2 in the definition of thresholds. So they just match, and we can adjust them. 1/2 is just a convenient choice. And this observation is straightforward from the definition, so let me not give you the justification, but let me give you how this observation connects to our examples. So let me remind you our second example. In the second example, X was n choose 2 and F was to contain a copy of K, where K is this H with a little tail. So in this 2 to the X picture, F looks like this. We have the empty graph at the bottom and the complete graph on the top. And F looks like, so we consider all of the labeled copies of K, and then we collect everything off of K. Okay, so this is the picture of F. Then, what happens if we apply our observation? So first, so we want to find a cover of F because we want to satisfy the first property. And an obvious choice for a cover is this. We collect all of the labeled copies of K. This way, G is simply the minimum elements of F. So obviously, G covers F, right? And in this case, if we do the computation in part 2, then we have this. And you'll notice that this is exactly the expected number of copies of K, right? Because we have Q to the size of S, so this is Q to the 6, and this is the number of potential copies of K. So this is exactly the same as the expectation calculation that we did in the first part, okay? So the second property is satisfied if Q is at most n to the negative 5 over 6. So this means this n to the negative 5 over 6 is the first lower bound from this cover. Okay? But we saw that we can do better. There is a better cover. Do you still remember that? What was the better choice? We can choose all of the densest part of K. So the second part, yeah. So our second cover is all of the labeled copies of H's. So in this case, if we go over the computation in item 2, then it gives us Q at most n to the negative 4/5. So this gives us a better lower bound. Okay. So this tells us that whenever we have a cover, it gives us a lower bound on the threshold. And so each time we choose a cover, it gives us a lower bound. And then the definition for the expectation threshold is this. We just choose the maximum Q that meets a cover. So we consider all of the possible covers, and so we consider all of the possible lower bounds, and then we choose the maximum. This is the definition for the expectation threshold. And of course, from the definition, this is a trivial lower bound on the threshold because we just choose the maximum among all of the lower bounds. Okay. Then finally, the rigorous statement of the Kahn-Kalai conjecture is this. So it says that there exists a universal K. So this is an interesting part. K is a universal constant. It doesn't depend on anything. It's like 72 or 3.4, like something. So this is a fixed constant such that for every finite set X and increasing property F, the threshold is at most K times the expectation threshold times log of the size of the universe. Okay, so this is the Kahn-Kalai conjecture. And okay, so next part is our results, but are there any questions?
So you say that K is a reasonable constant?
K is, yeah, it's not semi-rate constant, it's reasonable, yeah.
Yeah.
So from our argument, yeah, so we used constant about around 1,000, but we didn't try to optimize, so it can be better. Okay, any other questions? Yes.
Usually this expectation threshold is easily obtained.
Oh yeah, that's a good question. But usually, I mean, for this graph theory, I mean, for those like interesting questions in the random graph theory, yeah, the expectation calculation is easy. But if we consider any arbitrary increasing properties, then usually it's hard. Okay, so in application-wise, it's easy, but yeah, you don't know about like.
If I want to say that this expectation threshold is like bigger than something, right? We need to prove that it's bigger than
We need an upper bound on the expectation threshold to apply this because
oh,
we don't
right,
have an
right.
upper
We need
bound.
the upper bound.
Yeah. So any cover gives us a lower bound on the expectation threshold, but to give an upper bound, we need something else. But there is a way to find an upper bound.
Uh-huh.
Yeah.
So from the definition, it's non-trivial.
It's not trivial. Yeah. Okay. So there are many good questions. Are there any other good questions or mediocre questions?
Oh yeah, one last thing. Maybe why did you define it as a max instead of like infimum or no?
Oh, this is a finite set, so maximum always exists.
Okay.
Okay. Any other questions? Okay. Let me move on to our results. So the first result is not the Kahn-Kalai conjecture itself, but this is called the fractional version of Kahn-Kalai conjecture. So in this statement, we use P star E, which is called the fraction expectation threshold for F. But let me skip the definition. Let me skip the definition in this talk, but very roughly speaking, the fraction expectation threshold means we replace the cover G by the fractional cover. So G can be viewed as a 0,1 function, which is defined on 2 to the x, and we just replace this 0,1 function by a real valued function. That's a rough definition of the fraction expectation threshold. Well, let me skip the definition, but from it doesn't move. Okay, from the definition, it's very easy to see that the fraction expectation threshold is an upper bound on the expectation threshold, and this is the way. This is one way to get an upper bound on the expectation threshold. And so the fraction expectation threshold is still a lower bound on the threshold. Okay, and a couple of years ago, so this was a conjecture of Talagrand, and this was proved by Frankston, Kahn, Narayanan, and myself a couple of years ago. So we showed the Kahn-Kalai conjecture, but we replaced the expectation threshold by this fraction expectation threshold. Oh, and also there was a small improvement. So instead of the size of the universe, we use L of F, which is the size of a largest minimal element of F. So let me explain a little bit more. So let's say this is our increasing property F. And for L of F, we consider all of the minimal elements of F, and then we take the maximum size. This is the definition of L of F. So in particular, if we consider a fixed graph, in that case, L of F is just a constant. So that means there's no gap between the expectation threshold and the actual threshold. Okay, so this is what we proved, and one thing interesting about this statement is So as a statement, this is weaker than the Kahn-Kalai conjecture because the fraction expectation threshold is an upper bound on the expectation threshold. But in all of the known applications, the expectation threshold and the fraction expectation threshold have the same order. So this means everything that's implied by the Kahn-Kalai conjecture is also implied by our weaker result. And this is why our weaker result was also very, very complex. And our proof is inspired by always Lobel, Wu, and Zhang, their breakthrough in Erdős-Girardot sunflower conjecture. And I'm going to talk about more details about this proof part tomorrow. So, yeah. So let me put, okay. And, okay, so after we got this fractional result, a natural question that was raised by people was this, okay, what's the relationship between the expectation threshold and the fraction expectation threshold? And as I said, in all of the known applications, the two, the expectation threshold and the fraction expectation threshold, they have the same order. And then the natural question is, are they equal? Are they always equal up to a constant factor? And this was actually conjectured by Talagrand, and he conjectured they are equal up to a constant factor. And so far, so of course this implies the equivalence of the Kahn-Kalai conjecture and the fractional Kahn-Kalai conjecture. So before we proved the recent result, it was regarded as the most likely way to prove the Kahn-Kalai conjecture. Because once we prove this, then we are done. But even simple instances of this conjecture are not easy to establish. So Talagrand suggested two test cases. And so those two test cases are like, it looks very simple, but even for those simple test cases, we needed some argument. So this was proved by, separately proved by DeMarco and Kahn and Frankston, Kahn, and myself. But this general conjecture is still open. We don't know. So then our new result is this. So this is conjecture by Kahn and Kalai and proved by myself and Huy Pham. So we showed this. There exists a universal constant k such that for every finite set x and increasing property f, the threshold is at most k times the expectation threshold times log of L of f, where L of f is the same as before. And our argument is simple and direct, and I'm going to introduce the proof part tomorrow. And our proof is inspired by our previous work, sunflower conjecture and fractional Kahn-Kalai, but our implementation is pretty different. And I'm going to try to introduce the difference tomorrow. Okay. So now, okay. So how much time do I have now? Is this 2 minutes or 12 minutes?
2 to 12 minutes.
Okay, so let me take 6 minutes more. Okay. Or 7? Okay, so this is, so okay, so now the last part is, okay, so now that we have the Kahn-Kalai conjecture, then what questions are remained? And one big question is this. Okay, so yeah, technically speaking, what we proved is just an upper bound. So it gives the threshold is in between the expectation threshold and the expectation threshold times log of something. And the question, so the natural question to ask is what characterizes the gap between the expectation threshold and the actual threshold? So can we characterize the gap? And if we can answer this question, then it would be great because we can give the threshold for any given increasing property. So, okay. So in many cases, the log L F gap is tight. And here I wrote some examples, but let me not read all of those. But let me just say, in many cases, this log L gap is tight, but there are some cases for which log L gap is not tight. And we regard them as a good test case just to answer this big question. So one example is the square of a Hamilton cycle. Okay, so this is an interesting question, so let me mention this. So we know what a Hamilton cycle is, right? So a Hamilton cycle is a cycle that covers all of the vertices. And the square of a Hamilton cycle means we add some edges so that each vertex is adjacent to its second neighbors. So this vertex we add this, and for this vertex we add this. So we add more edges so that each vertex is adjacent to its second neighbors. And in this case, if we compute the expectation threshold, then we have n to the negative 1/2. But it was conjectured that the actual threshold is also n to the negative 1/2. So there's no gap. So this means this result is not implied by the Kahn-Kalai conjecture, because the Kahn-Kalai conjecture gives an upper bound with log n gap. And so you see this series of improvement on this result. So the initial one was n to the this plus little of 1, and then you see log n to the 4, log n cubed, log n squared, and log n. So this problem got lots of attention, and a couple of years ago we proved this right threshold. And one thing interesting is for this work, we slightly modified our proof for the fractional Kahn-Kalai conjecture. So this means we have some hope that we can modify our proof argument to get a better bound for specific problems. And yeah, another example is this. So here, if f is to contain a triangle vector, where a triangle vector means we have these disjoint triangles that cover all of the vertices. This is called a triangle vector. And in this case, the expectation threshold is n to the negative 2/3, and the actual threshold is this. So we have this strange fractional exponent. And of course, this is also not implied by the Kahn-Kalai conjecture. And for this one, we don't know how to do this using our argument. So that's one thing that we try now. And for the second one, okay, do I still have time? Okay,
Yeah.
okay, let me introduce this. Okay, the second one is a little bit different direction, but I think this is also interesting. So in the Kahn-Kalai conjecture, why do we have log n? And we suspect that this comes from the coupon collective behavior of the random graph. And what if we exclude the possibility that there is coupon collective behavior? So this k-out model means we start with n vertices, but unlike the GMP, what we do is each vertex choose its mate, choose its neighbors. So for example, if we say 2 out, that means each vertex chooses 2 neighbors. So 2 out looks like this. So in this model, there's no coupon collector because every vertex has a neighbor, right? And if we consider this model, which excludes the coupon collector behavior from the beginning, then what's the threshold for having a perfect matching? And it was shown that if k is 1, if each vertex chooses 1 neighbor, then there's no perfect matching with high probability. And if k is at least 2, then with high probability, k out has a perfect matching. So this k equals 2, this corresponds to p is about 1/n, so there's really no log n gap. And our question is, okay, then if we consider, can we get this result from using our argument? And if we can do that, then that means really the coupon collective behavior causes the log n gap. And we don't know how to do this, so this is another direction that we are thinking about now. Okay, so yeah, thank you very much. This is what I have for today.
Thanks for the very nice talk. Questions?
For the last case was like regular graphs, not more general, and then the bound is maybe a tree.
Oh, you mean the k-out model?
Yes, because like if all of them have like out degree 2.
Oh, random regular graphs? Are you asking about random regular
Yeah, indeed,
graphs?
because like with k out, the final, if you consider it as a graph again, it does not have to be regular, but maybe regular graphs are more common, and over there like the average degree will be 4 with k equals 2, so like 3 might be the...
Oh, so for regular graphs, we know a lot. So yeah, basically for random regular graphs, we know a lot. For this k-out model, we know this perfect matching. So the reason why we are interested in this problem is we know about the perfect matching in k-out, but if we consider the hypergraph version, then we don't know the answer.
So k out is harder than regular.
Yeah.
And
And because here in K out, yeah, so the lack of regularity causes the problem. In this K out, the degree distribution is Poisson, so this is not regular.
So the fractional threshold, expectation threshold, does it have the LP duality and ABS? Does it have any combinatorial meaning?
Combinatorial meaning.
You mean the dual problem?
Right.
Yeah,
What's the meaning of the dual problem?
Yeah, of course we use the LP duality and in our proof. That's true. And if you ask combinatorial meaning, I don't know. So it's very natural to move from the integer problem to its fractional version problem, continuous problem. And other than that, I don't know what exactly you're asking.
So for example, transversal and matching,
Mm-hmm.
and they both have combinatorial meaning, and their fractional version are the same. So I wonder
Ah.
here.
So it's more like we move from, because integer problems are usually very hard, and in that case we move to the continuous version of the problem. So the fractional expectation threshold is more like that. So yeah, because once we move to the fractional expectation threshold, then we can use the LP duality, and from there, I don't know if you're familiar with this. From there, we can move to the spread of our hypergraph, and that gives an upper bound on the fractional expectation threshold. So yeah, so in that sense, it has some combinatorial meaning. I mean, in the sense of spread. Yeah, if you're interested, then I can tell you more, but now is not good.
So is computing the fractional threshold easier?
So what usually happens is we know how to compute an upper, so there is a way to compute an upper bound on the fraction expectation threshold. And so that means usually in many of the applications, this upper bound matches the lower bound. So we have the I don't have.
Oh yeah, the chalk.
Okay. So we have the expectation threshold and the fraction expectation threshold, and we know this. And there is an easy way to get a lower bound, because whenever we have a cover, it gives a lower bound on the expectation threshold. And there is an easy way to get an upper bound, which is called spread. But I didn't explain what this means. It takes a little bit of time. And in many applications, this and this, they match. So this lower bound and this upper bound just nails down the value of the expectation threshold. Yeah, up to a constant vector. Yes.
And this type of finding can be extendable, assuming the graph is not a random graph, but like scale-free graph.
What graph?
Like a scale-free network with preferential attachment, like edges are generated.
Okay, so changing the random model is pretty delicate. So that's why I mentioned the very last example, very last question. So if we move from binomial to K out, then we don't exactly know how to do that. So changing the random model that's an interesting direction of research. But we have to think about that. So yeah. So that's another thing that we can think about.
Okay, question? No. Right. If not, let's thank the speaker.